Good morning, everyone.
Good morning.
Good morning, Sis.
Morning.
Good morning. How are you?
Good. Good morning, sir. We are just about 14 in number, and I think we are good to start anyway. I mean, we're expecting more people. we have well over 20 people who are already participating in this training. I guess they'll keep joining us as we continue. So good morning, everyone. Without wasting much time, we're already 3 minutes behind our schedule, and last week we lost about 30 minutes, and for that reason we couldn't finish our presentation for last week. So we're just going to continue from where we left it last week. Notwithstanding, I'm sure I've discussed this with Uche and Engineer Uche, and we have enough time to cover up, the entire training module. We'll definitely cover all. But what I don't want to do is to rush the process. We're going to take it, slow and steady. We're going to make sure we cover everything that we've prepared to go through. So I'll start sharing my screen now, and so we can just start. Can you all see my screen?
Yes, we can see your screen, sir.
Okay. Thank you very much. I mean, so let's continue from where we left since last week. We went into electrical energy before our time was expended, and unfortunately, I have to end the class just to allow other people to fulfill their scheduled activities. So today we're going to continue from here, talking about electrical energy. In the previous week, we talked about energy as in general, renewable, non-renewable, energy conservation, and all that. Now let's dive into electrical energy. As we progress, we're also going to talk about other forms of energy, maybe chemical, thermal, mechanical. That's when we get into the industrial application. But for now, let's stick with electrical energy. So there are different things that makes up what we know as an electrical energy. I don't understand what's going on. Who is Jide? I don't know. He's interfering with my screen here, and I don't know what's going on here. Okay, so back to the basic electricity and all that makes up the electricity. So we talked about voltage and current, and I tried to explain this using the water and pipe analogy. And I explained that what we actually consume is the current, not the voltage. So the current is synonymous to the water that flows through the pipe, and the voltage is synonymous to the pressure that pushes the water through. So what you actually consume, what your equipment consume is the current. It's good to have this clear understanding of electricity, and the current is basically electrons. That's what they are. So electrical power is when voltage and current work together to do something useful, such as turn a motor or light or light a lamp. And then the formula for calculating electricity or electrical energy is the unit is watts, which is voltage times current in amperes or amperage times power factor. We discussed this last week, so I'll just go on with the various forms of electricity. We have we have single phase electrical systems. So various forms of electrical system. So we have a single phase electrical system. For most of us in our homes, if you're for those of us that have a small house or you're living in an apartment, basically you're most likely going to be on a single phase because most of the equipment in your homes, in fact, most of the household equipment are single phase system. There is this conception that when you have three-phase system connected to your home, then that means that you're using a three-phase, or that you have three-phase. It doesn't mean, even if you have three-phase connected to your home, unless you have three-phase equipment. I would explain the concept of three-phase equipment, but for most of our homes, what we have is single phase, and for the fact they have the whole wire coming into your home does not mean that the entire phases are connected to your house. You only connect to one phase at a time, right? And so sometimes there might be outage on one phase, and you want to switch over to another phase. For those people that have that, that flexibility. So we are going to talk about the single phase. So this is a system having only one sine wave, and the frequency is about 50. In Nigeria, we use 50. In some other places, I think America uses 60 hertz, but we use 50 hertz in Nigeria. So it depends on the country. So and this is what it looks like, and this is why it is called. So we have two kinds of current. I didn't say this, but maybe I assume that some of us already know this. So we have two kinds of current. We have AC current, alternating current, and we have DC current, direct current. So, but what we're dealing with here is an alternating current, which is the AC current. Okay. When we get to the solar side, when we start talking about solar system, we can also talk about DC current, because solar systems produces direct current, which is DC. That's why you need an inverter to convert it from that DC current to an AC current. But now let's dwell on the AC current. So AC current means alternating current, and you can see from the sine wave, it's alternating, and that's why it's called alternating current. DC current are not alternating, they're just straight lines. Okay, well, this is an AC current. So this is a single phase voltage system. Now we have a three-phase system. So this is a system having three sine waves, and frequency of each sine wave is either 50, like I explained. The same with AC current. In Nigeria, we use 50 hertz. In America, it's 60 hertz. So the three sine waves are separated in time with a phase angle of 120 degrees. Phase angle of 120 degrees. So you can see the three phases. So you have the blue, the red, and the yellow phase. So these are the three phases. So for equipment that uses three phase, what usually happens that you have these three phases connected to the equipment directly. So not just one phase, the three of them are connected. Now that depends, how these are connected depends on the type of connection and the type of equipment. Okay, without going too technical, there are different kinds of connection for three-phase system. There is delta connection, there is a star connection. But I don't want to go into, when we get to the industrial part of it, we can talk about it. But just know that there is a single phase and there is a three-phase. And for three phases, the three wires, the three phases, the three are connected to the equipment all at the same time. So let's talk about power quality. Power quality is related to how well electrical system maintain a pure sinusoidal waveform at rated voltage and frequency. Now, sometimes many of us will complain the quality of the power electricity that we get in our homes or in our factories. You will notice that some industry, they don't want to remain on the grid because of the quality of the power. Some equipment, especially industrial equipment, they are sensitive to the quality of the power. So if they're not coming at the specified quality, it affects, because this equipment has been designed to work at a certain specifications of the power in terms of the frequency, the voltage, and harmonics. So the system has, the equipment has been designed to, but when the power that is coming is not meeting that specification, then you run into problems. Okay, the equipment begins to malfunction, and we're going to talk about it anyway, but just a general overview of what power quality means so we can understand what we mean when we talk about power quality. It's cost across so many variables, and we're going to look at these variables. So power quality issue involve all momentary phenomena, including spikes and outages, as well as harmonics. Outages is also a component of power quality, because when you keep having frequent outages, it affects your system, especially for sensitive equipment. So modern electronic equipment both causes and is affected by this problem. Power quality is becoming one of the most important issues in energy management. So, I don't want you to lose sight or lose focus of why we are doing all of this. We are doing all of this such that you are able to manage energy, not just electricity. You're able to go into a facility and understand how energy works, how energy flows. If you understand how energy flows in a facility, remember, energy is not visible except in the form of light. I think that's the only form of energy that is visible. You can't see energy, you can't see electrical energy, you can't see some of these things. So because you can't see them, you need to understand how it works. And when you get into a facility to conduct an energy audit, you should be able to understand what is going on in that facility. Maybe with the help of some few or some certain energy auditing tools, you can just check to verify something. But essentially, you should understand generally by looking at the facility and just understand at a high level what's going on. Then it's now going to inform your knowledge of how you can then narrow down to where to do your testing to verify some certain things. Okay, so all of this is required for you to be able to manage energy and identify losses and curtail those losses. Even as well as recommending efficient equipment or more efficient equipment. So all of these are very necessary, and that's why we're talking about this. So now let's go into harmonics. Harmonics are a distortion of normal electrical current wave, generally transmitted by a nonlinear load. So what are nonlinear loads? Nonlinear loads are nonlinear loads are solid state devices. So think about electronics, for example. Every electronics is a DC, are operated on a DC current. Your television, your radio, any electronics you can think of, they are operated on a DC current. So what happens is that your AC current is coming into those electronics, and those electronics have to convert them to a DC current to function. So in the process of converting that, you now have so those are the linear load. I mean, those DC equipment that are running on AC system. I mean, on AC circuit. So these are the non-linear load. Sorry. So in other words, they're not solid state. They're solid state equipment. So in other words, harmonics are multiple of fundamental frequency. Okay, so remember when I talked about frequency, and I said that our frequency is 50 hertz. 50 hertz. So now let us see how harmonics affects that frequency. Because harmonics is something that is not in the front burner. It's not like voltage. It's not like current. It's not like power factor that we all know. It's on the hint side, but it affects the electrical system a lot. So so if the fundamental frequency is 60 hertz, now if this is an American system where you have a 60 hertz, now there's what we call first harmonic, second harmonic, third harmonics. I will explain that in the next slide. But just understand that if you're talking about a second harmonics, what it does, it doubles your normal standard harmonics. So if your harmonics is 60 hertz, your second harmonics will be 120 hertz. Instead of maintaining your 60 hertz, your second harmonics will be 120 hertz. Your third harmonics will be 180 hertz, and it will continue in that order. So for Russia and Nigeria, our fundamental frequency is 50 hertz. Second harmonic will be 100 hertz. The third one will be 150 hertz, and then so on and so forth. Now, this is how it happens. Now, this is our standard sine wave, right, for a single phase. This is our standard sine wave. Undistorted is a normal, is a fundamental sine wave. Now, let's see when harmonics comes in, how these waves behave. Now, the red one, which is the first one, is our fundamental wave, right? Now, let's let's explain this using a third harmonics. And when I say third harmonics, that means that it's a multiple of 3. So instead of 50 hertz, you're now having 150 hertz. So this is what happens. When harmonic comes, it tries to distort this your fundamental frequency, right? Such that it goes like 3 times before it actually completes one cycle. You can see what the harmonics is doing here. It's distorting this red one. It's actually distorting it. And now the actual frequency that you now have, I mean, your final output now becomes this blue one, which is now your third harmonic. So you can see that before you complete one cycle, it's already completed 3. And that's why it's a multiples of 3. So for a second harmonic, if it's a second harmonic, this will only be completed 2 times. So this will be 100. Okay, so this is how harmonics distorts your sine wave electrical current systems. So in the end, this is what you now have. So this becomes your distorted periodic wave. This is the fundamental. This is the standard. This is what it should be. But when harmonics comes in, it distorts this wave, and this is what you have. And then it affects your system, your electrical system that are sensitive. So what are the causes of harmonics? Harmonics are generated by solid state-based equipment, just like I explained. I already explained this even before now. They are generated by solid state-based equipment, such as your switching power supplies in your PCs and other electronic systems, your DC drives, your variable frequency drives, your electronic ballast, your arc welder. So if you look through this list, you will realize that all of these items listed are things that convert your alternating current to a DC current. And the same thing goes with your LED bulbs. Now, if you remember, the LED bulb that we all know today, that is the energy efficient bulb or the energy saver, is an electronic device, it's an electronic system. So what it does, it converts, because it's an electronic system, it converts your AC to a DC. So your LED bulbs actually introduces harmonics into your power system, but I think it's minimal. I mean, and that's why sometimes you need to measure the level of harmonics in your system. And if it's already affecting the devices, then it needs to be dealt with. There's a way to deal with it using harmonic filter. So most power systems can accommodate certain level of harmonics, just like I explained. For your LED bulbs, yeah, they introduce harmonic, but at minimal level, the system can still tolerate it. Now, but we experience problem when harmonics becomes significant component of the overall load. Now, as this higher frequency harmonics current flow through the power system, now they cause communication errors, especially if you have IoT devices. You know, IoT devices, sometimes they work with the signal, the electrical signals. Okay, so but when the current is distorted, it also affects the communication of this IoT system. And it also leads to overheating. Of course, the hardware can get damaged, and then metering error as well. So all of these are things that can also, be caused by higher level of harmonics. So in trying to determine in power quality, when you look at power quality analysis, what you're going to see is total harmonics distortion. So they measure the total harmonics distortion in the system, right? That's how it is measured in a power quality analysis. Now, when you notice that you have a higher THD, what is the solution? The solution is harmonics filter. Okay, you introduce the harmonics filter, just like you have to filter them out and then correct that signal, that sine wave, back to its normal and fundamental frequency. So what is harmonics? These are just series of parallel resonance circuits designed to shunt or block harmonics current. So now we've talked about harmonics and how it affects electrical systems. Now let's talk about voltage. Remember, every country have a standard voltage. Here in Nigeria, our household equipment, the last mile consumers, our voltage is 230 volts. 230 volts. Yeah. So when you go to the distribution network, we have different levels of voltages. From the power plant, the electrical currents leads the power plants into the national grid. The highest voltage we have in the national grid is 330 kV, kilovolt. That is 3,300 volts or 330 kilovolts. That's the highest level. But along the line, you begin to step it down through the substations, transmission substations. And then before it gets to your house, it gets stepped down to 230 volts. That's what your appliances work on. So it has to come down to that level. Okay, so problems can occur because of voltage imbalance. Now, when we talk about voltage imbalance, I want you to bear in mind that when we are talking about a single phase system, voltage imbalance is not really necessary. We only talk about voltage imbalance in a three-phase system, and I'm saying this because most industrial equipment run on three phase, especially the industrial motors. Especially industrial motors, they run on three phases, right? So it's important that you look at what are the voltages of these phases going into this industrial motor. If there's a variation in the voltages, right? If there are variations, it can lead to problems in those in the functioning of those motors. And this explains the reason why most of these industries in Nigeria, they try to avoid the grid for some reasons, not just voltage. Sometimes the voltage that is coming in is not sufficient to power the equipment. That's one. Two, because of the frequent interruptions, of the grid. You don't know when the grid is going to be interrupted, and you might be in the middle of sensitive production, and all of a sudden the power goes out. Okay. Now you don't just lose money; you also lose material, because if it's a production, and in some cases you need to clear out some of the things that have been stuck in your production system to start the system again, to start the system. So you're not just losing money; you're losing resources in terms of the materials that are being wasted. You're also losing time, because the time you're going to spend to clear out, and so all of these are the challenges of running sensitive or industrial processes on the grid. It comes with its own risk. So sometimes most of these industrialists, they prefer to just have their own alternate solution, maybe generator, gas or diesel generator, that they know that they can control and it's more reliable. Now, percentage voltage imbalance is found as a ratio of the. Now, I'm talking about how do we know when there's an imbalance in voltage? How do we calculate it? What can be done? So percentage voltage imbalance is found as a ratio of the largest face-to-face voltage, the largest face-to-face voltage difference from the average divided by the average voltage. Now, I'm going to explain all of this grammar. So for example, if we have 220 volts. Now remember that the standard voltage for Nigeria is 230 volts actually. So, but if we have three phases that are going into an equipment, and the voltage across these phases are 220, 215, and then 210 that are going into this equipment. Okay. Now all of these voltages are expected to work, harmoniously to perform or to enable the equipment to function. But you can see there is already a level of conflict on the level of voltage that is coming into this system. So it creates problem in the system. Now, how do we know the level of imbalance in the voltage? That's what we're going to do now. Now, the average voltage is, you add all of them and divide by 3. That's so you find the mean or the average of the voltages. So you have 220 plus 215 plus 210, you divide by 3. So you arrive at 215 volts. So that's the average, right? Now, the next thing you're going to do is to find the difference. How does each of these line voltages, how do they vary from this average voltage? So what you're going to do is you're going to do subtraction, right? So you're going to now subtract this average voltage from each one of the line voltages. Okay, so the first one is 220. So you're going to subtract 215 from 220. So when you do that, you have 5 volts. So the difference there is 5 volts. If you do that for the middle line, the difference is 0. 215 minus 215 is 0. Now for the third line, is going to be 210 minus 215. So it is minus 5. So bear in mind that the negative, the minus is insignificant. It does not really matter because it's an alternating current. So it's plus, minus. So it's going to definitely cancel out. So whether plus or minus, it doesn't, I mean, it's irrelevant. Now, what you're going to do next is that I've already explained this, whether positive or negative, it is irrelevant because it's alternating. Now, the voltage imbalance is therefore the highest difference among the three phases. So the highest is 5. Okay. If this were to be minus 10, it will be the highest. I mean, the minus does not really, is insignificant here. If it were to be minus 10, then it becomes the highest. So, but in this case, we have 5, which is the highest. So we divide 5 by the average voltage, which is 215. When you divide that, you have 0.023. So in essence, it is 2.3% difference. I mean, voltage imbalance. 2.3%. So when you have a voltage imbalance of 2.3%, I think it's becoming significant somehow. Because for me, I think 1% can be tolerated, but if it begins to go above that, I think it's something that needs to be controlled. Now, the reason why you have this voltage imbalance in some cases is because you have certain load concentrated on one line. And that's why for people who are in electricity distribution business, this is important for them because they want to make sure that at every point in time, none of their phases are overloaded. So for example, if your red phase is overloaded, okay, what that means that you're going to have more loss because once it's overloaded, you're going to have higher heating on the cable and it's going to result to higher losses. So your technical losses will actually increase and you lose power along the distribution network, right? So that's one problem for it causes for the people who are in electricity distribution business. But for you who is at the consumer side, it also results to damage of your equipment or improper functioning of your equipment. And that's why it's important that we do this. Now, if you got a facility and you notice there's a voltage imbalance at significant level, what that also do, it also makes the customer to lose, I mean, the facility or the industry to also lose money because after your meter, once that power has passed through your meter, every losses that happens after your meter, you have to pay for it. But if the losses occur before it comes through your meter, it's none of your business. But once it passes through your meter, mind you, once that current passes through your meter, the losses will continue. If that voltage imbalance is there, the losses will continue, but those losses will not be on your bill. And that's why it's important that you identify them and also find a way to manage them. So, okay, before we go into this example, I'd like to talk, okay, how do you deal with voltage imbalance? Essentially, you deal with voltage imbalance if it's because sometimes there's a limit to how you can manage this voltage imbalance. Sometimes you might need to contact the utility or the service providers so that they can also try to balance this voltage. Now, balancing the voltage is essentially trying to distribute the loads across the three phases. Okay, so maybe a certain load is concentrated on one line, maybe the blue, yellow, or red phase. If too many loads are concentrated, so it will also affect the voltage across that line. And then for the other two lines, they will have a lesser voltage because they have lesser load. So essentially, what needs to be done is to move some of the load from that overloaded line, spread them, and then keep monitoring the voltages until you have an evenly distributed voltage. You may not have a perfect, but of course, the variation shouldn't be so much that it affects the functioning of your equipment. So that being said, let us look at an example. We are just going to replicate what I did, the solved example I already discussed. So if we have 400, 385, and 409 volts, the voltage imbalance is what? Now, let me also explain this because we need to understand the levels of voltages that we have. Okay, I have mentioned that the household, the voltage that we use for single phases or in our homes is 230 volts. That is the standard voltage in Nigeria. But before I get to that, there's another level of voltage, which is 400. In Nigeria, it is 400. It is not 415. There has been a lot of misconception I don't know how this, I think probably because of the documents that we use in developing our electricity system, we are that of the British, so I think in Britain, I think they have 415 as their voltage, as their line-to-line voltage. But here in Nigeria, it is 400. Okay, that has been, the regulator has been trying to correct this, as well as the government, the people in charge of importation. When you go for your clearance or approval, sometimes they also have to look at your voltage level in terms of maybe your transformers. Now they are trying to correct. If you're importing a transformer that is 415, I think it will hardly be approved also, because they're not trying to correct this error. Our voltage, our standard voltage, line-to-line voltage is 400, not 415. And if you do the root 3 of 400, you're actually going to get that 230, and that's how you get the 230 volt that we have. If you do 415, you're going to land at 240. So if you're using 415, what that means that our household or our line to neutral voltage becomes 240 instead of 230. I'm saying this because it's important as an energy manager or as an energy auditor. It's important that you understand some of this so that you don't get uncomfortable when some certain questions are being asked to you, maybe by your client, or in other words, for you to be able to explain some of this to your client such that they are satisfied or they can understand. Okay, so now this is line-to-line voltage. The example we used in the previous one was line to face line to neutral or face to neutral. Okay, so this is the next voltage level. Before it actually comes to your house, it's at 400. Okay, but the moment it's coming to your house, it then splits and then becomes 230. So now we want to calculate the voltage imbalance across this line. So we have 400, which is the standard voltage. We have 385, which is lower than the standard voltage, and they will have 409, which is higher than the standard voltage. So how do we calculate the voltage imbalance? The same way we did for the example we did. We have to find the average from the three phases, right? And then we divide. Okay, we now subtract this the average from each of the voltages, and they will determine the highest deviation. I will divide by the average. Okay, so I didn't break down the solution here, but you might want to do it. If you have pen and paper, you might just want to do so, but in the end, we're going to arrive at the same answer anyway. So what we did here was we look for the average of 400, 385, and 409. If you add these three figures together and divide it by 3, you're going to get 398. 398. So if you now do the subtraction, let me get my calculator so we can do this together. Okay, so if we now do 400 minus 398, you're going to get 2 for the first one. Then for the second one, if you do 385 minus 398, you're going to get minus 13. And then if you do for the last one, which is 409 minus 398, you will get 11. So the highest deviation is 13, minus 13 on 13. That's the highest deviation. So we take that highest deviation and we divide it by the average voltage, which is 398. So when we do that, we're going to get 0.033 or 3.3%, which is higher. It's high anyway. It's significant and needs to be managed, needs to be balanced. So these are further examples you can try. I mean, the answers are there. You just have to follow the same process that we used to calculate it, and they see that if you arrive at the same answer or not. If you don't arrive at the same answer, then your process, something is wrong in the process. So what are the problems with imbalances in voltage? Okay, so you could have electrical equipment overheating, just like I have explained. It starts from your lines, your network, your wires. your wires begins to overheat, and that heat that is happening on your lines are losses. I mean, you keep losing money. So there could be electrical circuit failures. You will have noticed that sometimes, even this happens a lot, you know that there's maybe a line goes out, from your distribution network. And the way you normally do, you want to switch phase. You want to go and change another line. So what actually happened for some of them, I mean, some of the reason why this is happening is that the line sometimes gets overloaded and it trips. Okay. So these are consequences of imbalance in the voltage. And also there's a reduced equipment operating life, and there's also production and operation impact for maybe for industrial applications. Now, this is for overvoltage. Undervoltage have similar consequences. So you have lack of sufficient power to operate electrical equipment. So when you have, some of us that have normal standard air conditioning system in your house, normal AC, not inverter type air conditioning system, just the conventional air conditioning system in your house, you will notice that when the voltage is low, your AC will not function. I mean, essentially, the compressor will refuse to work because the voltage is not sufficient to carry the compressor to kickstart it and keep it running. The voltage is not sufficient. And for the way most of us have dealt with this problem is that you get a stabilizer. What does a stabilizer do? A stabilizer actually just increases the voltage. It augments that voltage so that your compressor can actually work. So that's what stabilizer do. And in some cases, when the voltage is higher than the required voltage, your stabilizer can also bring it down. So that's what stabilizer, that's their function. That's why you need stabilizer in some of these cases. And some equipment that can tolerate it, okay? Maybe inverter AC. I mean, if you're using an inverter AC, so I mean, they can tolerate it in as much as it's not the standard voltage, but sometimes some of your equipment can tolerate, some of this under voltage. So there is also a problem of electrical circuit overheating. There's a reduced motor torque. If you notice, if you have in my house, because I have solar system as well, and so when I'm on the grid, I will notice that my fan, my fan reduces, the speed reduces. But when I'm on solar, I mean, because the solar is actually giving me the standard voltage, my inverter is giving out the standard voltage, I will notice that the speed increases. But once I go to NEPA, sorry, I keep saying NEPA, of course, we all understand what I mean by NEPA. But when I go to the grid, the rotation reduces, because the voltage is not actually, to that, standard level. So for industrial application, it gets, the motor gets overheating, it reduces equipment operating life and production and operation impact as well. So these are the issues, these are the problems that can happen when you have this, imbalance in voltages. So let's talk about power factor. Power factor. It's a big issue. Power factor is a big issue. For everyone, both the grid utility provider, I mean the NEPA or the AEDC or Ikeja Disco or Eco Disco or I mean whatever it is that is providing you the grid supply, is a big concern to them. But I don't know if that's a big concern to them in Nigeria. But outside there, in other world, it is a big problem. And I say this because they often impose penalties for people who actually create this problem for them. Yusuf, you asked a question. If is that load shedding? Sorry, I'm just reading your message. I mean, can you clarify, please, so I can explain. I didn't understand. Maybe you asked this question at a point when I was explaining, but I mean, I'm sorry, I'm just reading this message.
Hello.
Okay, go on, please.
Okay, I think that was while you were explaining the voltage imbalance at the distribution company end.
Okay. Yeah, okay. That's not actually load shedding. That's a fault on the grid. I mean, it's a fault. And in this case, the provider needs to rectify the fault. In that case, what they would normally they will try to balance the voltage when a line goes out. Now, load shedding is different from what is happening here. Okay, load shedding is essentially when you have more people who wants electricity, just like the case in Nigeria. We have a lot of people who are demanding for this electricity, but the generator is not enough. I mean, the power that is coming from the generator is not enough to give to everybody. So in that case, you need to, you cannot give to everybody at the same time. So you can give to Mr. A and B at the same time, but you cannot give to Mr. A, B, C, and D at the same time. So you can only give to A and B at the same time. And another time, you take the power from A and B and give to C and D. So that is load shedding. You keep alternating them, keep managing them, unless up until the time when you have additional generator or generation that can cover, A, B, C, and D, then you can say, okay, now you have to stop the load shedding and give everybody at the same time. So essentially, that's what load shedding means. So now let's talk about power factor. Like I said, I was saying that power factor is a big issue for the utility providers, but I don't know how big of an issue it is for the Nigerian people. Based on some of the conversations I've had at various levels, even at at all levels anyway, the feedback I'm getting is because more than 50% of the consumers, of the grid consumers in Nigeria, more than 50% are residentials, right? So because they are residential, power factor is not really a big issue for Nigeria, because essentially power factor becomes big issue when you have industrial equipment. It becomes, it becomes a big issue. And that explains the reason why in Nigeria, I mean, the utility companies, they're not so big on power factor, okay? Because a lot of people who are consuming this power are residentials, and they don't have heavy equipment, they don't have three-phase equipment, and so for that reason, it does not so much impact. So we're going to discuss power factor so they understand what power factor means actually, and then by understanding what power factor means, then you can actually make sense of what I'm saying now, that is actually attributed to mostly industrial facilities. So let's just go on. So power factor indicates how well, when we talk about electrical current, I spoke about two things. I talked about voltage and I talked about current. So now power factor is something that tells you the relationship between these two things, okay? How well the voltage and the power, the voltage and the current, how well they are working together. So it's like a marriage. So electrical system, electrical current, not current, electrical power is like a marriage between current and voltage. So if they're happy together, everything is going well, you will know from the power factor. If there's a conflict between them, the power factor will tell you there's a conflict between them. So it's an indicator that tells you how healthy that relationship is, right? So it indicates how current and voltage are working together, a number that ranges from 0 to 1 or from 0% to 100%, okay? So how do we calculate power factor? So power factor is equals to kilowatt, which is your actual power or your real power, divided by your apparent power. We're going to explain in the next slide also, we're going to explain all this, what your real power is, your apparent power is, and so we're going to explain all of this. But just have in mind that if you want to calculate your power factor is your kilowatts, which is your real power, divided by your apparent power. Now, apparent power, this is kVA. You will realize that generators are rated in kVA because that is apparent power. That is all the power they can give, irrespective of what your power factor is, okay? But the actual power that you can get from that generator is now where the component of power factor comes. So your power factor reduces what you can actually get from the generator. So your power factor reduces it, right? So this is what your generator can give. For example, your generator can give 100 kVA, 100 kVA. If your power factor is 0, if you have a 0 power factor, what that means that your 100 kVA will give you 100 kilowatts. But as long as your power factor is not 0, it reduces the power you can get from that generator from 100 to maybe 80, 70, depending on where your power factor is. So just we can understand how power factor reduces the capacity of our generator or the capacity of our transformers. Now, the ratio of how much the power supply that can be used to perform useful work, you know. So power factor is dependent on the type of load on the electrical system. We're going to talk about these things that affect the power factor. Please, if there's any point you want maybe further clarification, please call my attention and we can talk about it. Please, I mean, I want this to be very. I want everybody to follow, and I want this to be to give as much impact as possible. Okay, so now power factor reduces the amount of use. Sorry. Is someone asking a question? Okay. So let's.
I want to ask a simple question. I
Okay,
didn't want us to waste time. The simple question goes this way: you say power factor is dependent on the type of load that is in the system. Is it just, for instance, we have a transformer and it's rated in kVA? Is it the transformer that is the load, or the load that is being supplied from the transformer to I mean the power that is being supplied from the transformer to a certain appliance, let's say industrial machine, your washing machine, or whatever? Is it the one that matters about the power factor, or the transformer itself?
Okay, thank you very much. Just hold the question. It's noted. In the comment slide, I will explain that. Okay, yeah, it is noted. But when we get to that point and I explain it, if you still don't understand it clearly, then please feel free to. But let's just take. We'll come to that. Assis is asking which device or equipment to measure voltage imbalance. So essentially, you have your voltmeter. I mean, it's just measuring the voltage across the lines. Okay, you have your clamp meters. You can just clamp it across the lines, and then you can note the voltages across the lines. Then once you have this voltage, then you have to now do your calculation. I mean, I don't know if there's, of course, there could be applications that can do those calculations for you, but it's a simple calculation that anyone can do. But what you need, the primary data you need is the voltages across the line, which you can use your clamp meters to determine. Okay, so let's continue. Your question will be addressed. Okay. So now we have three types of power. Three types of power. We have kVA, which is apparent power. We have kilowatt, which is the active power or the real power. Now, this is power that performs the work. Okay. Now, kVA is what you pay for. Okay. Now, kilowatt is the actual power that you use. Now, kVAR is a reactive power. It does not do any useful work. And we're going to use beer analogy to explain this. If it's in the next slide. Okay, now let's address the issue. Let's dive more into the power factor. Let's understand the kinds of load and how it affects power factor. So we have these different kinds of load. We have three kinds of load. We have resistive load. Resistive load. Now, in an electrical system, volts and current both ideally have a sinusoidal waveform. So this is an electrical system. This is a single phase and electrical system, right? Now you can see that the red one is the voltage, the black one is the current. Now both of them are moving in a sinusoidal waveform, right? Now, if the current and the voltage waveform are aligned and reach their maximum amplitude at the same time. What is amplitude? The amplitude is the highest height that they can get. The highest height. So you can see that the voltage have a higher height than the current, but that's not a problem. Now, the good news here is that they are working harmoniously. So now, in this case, both of them will get to their maximum amplitude at the same time. The current is said to be in phase with the voltage, and there is no kVAR present. So what that means that in this case, your power factor is 0. So the moment your voltage and your current reaches their maximum amplitude at the same time, now this is their maximum amplitude. This is it for the voltage and this is it for the current. They both get to their maximum amplitude at the same time, irrespective of the fact that voltage has a higher amplitude than the current. But what matters is that they both, sorry?
Power factor is 1, not 0.
Yeah, thank you very much. power factor, so what that means that power factor is 100% or 1, just like he said. Power factor becomes 1 or 100%. Okay. So thank you. So that's what it actually means here, that both of them get to their maximum amplitude at the same time. So they're working, I mean, their marriage is going on very well. I mean, they are enjoying their marriage, no issue. So now the question is, what are resistive load? Okay. So an example of a resistive load are heaters. Every heating element are resistive load. If you remember the yellow bulb, the yellow light bulb that we used to have, you know, the incandescent bulb, like some of us call it, is a resistive load. Okay, and because of that resistance, that's why you have that glow that actually, you know, creates the visible light that we use, right? But it's more of a heating element than a lighting element. And that's why when you see those yellow bulbs, when you feel it, when you take your hands closer to them, they are very hot because they are more of a resistive load. And that's why technology, over time, technology begins to change and improve. And now we have the LED, which is a more lighting, you know, device. Okay. So the heater that you use in your house to cook food, the electric heater that you use to cook, those are resistive load. So what it does, it converts all the electrical current that is coming in, it resists them and they convert them to heat. Okay, so these are resistive load. And when you have resistive load, your power factor is perfect. It's 1, it's 100%. Okay, so now that's one kind of load. Keep that on one side. Let's look at the other type of load. Now we have an inductive load. Inductive load. So, however, if the voltage reaches the maximum amplitude before the current, so now look at what's happening here. Now this is the voltage. It gets to the maximum amplitude before the current. Okay, so it has left the current behind. The current has left the voltage. So they're not, the point that both of them are not getting to their maximum amplitude at the same time. So there's a problem in this marriage. Okay. So in this case, the power factor is not perfect. So the power factor will tell you that, look, there's a problem in that marriage, in the marriage between voltage and current. Okay. Now, when this happens, then your power factor becomes lagging. So what that means that your power factor begin to reduce. So it's less than 100%. It's less than 1. That's what happens here. Okay. So what are inductive load? Your inductive load are your motors. Your motors can be found everywhere. Even in your phone, you can find motors in your phone. But motors are everywhere. Your electric fans are motors. But these ones, they don't actually have so much impact on the electrical system. Where the problem begins is when you have an industrial application. Now, for industry, they have large motors, very large motors, right? So this is where most of these problems begin, because they begin to now affect the power factor of the electrical system, right? So these are inductive load because they need, extra, current to get started, and there are flux that, the way the system is designed is actually, meant to, take more current.